Yes.
Thank you, Sonia.
Thank you, Rolf. Then I will start with the next topic. So during my presentation, I will go a bit more deep into the antenna calibrations, which we're using within the IGS. Before I want to go too deep into the antenna issue or why we have to use them, I just want to mention what is the IGS, in particular the IGS working group and the center we're doing in order to collect those antennas and give them to the analysis centers and the users. So on the one hand side, the IGS is coordinating the antenna and receiver names among the calibration facilities, site managers, and ACs. So we have to make sure that if we identify an antenna, everyone knows how to name it, so we know which antenna is meant. The second part, if we have these antenna calibrations, there we have elevation and azimuth dependencies. So it's also very important to know how do we have to align the antenna. So to which point is the 0 degree kind of the pattern. And the last and not least, of course, is the IGS also then maintains the antenna patterns itself, which are always have to be used consistent with the current reference frame. So currently we have the IGS 14 antex, and this is processed in collaboration between the antenna working group and the reference frame, as it kind of includes the scale, which you will get when you do then a PPP solution. And all these files can be downloaded on the IGS website. Now, as Rolf has mentioned at the beginning, when we look at the equation of the phase, we see we have the phase, then we have the geometry, and then some other terms. I am just interested now in the geometry. Here we have the satellite position and the receiver position, or basically the antenna position, and then we create distance between those two. And first I want to go into the issue about the receiver station. So there, as you probably most know, meanwhile, as Rolf already mentioned it, we have an antenna, and the antenna has a physical antenna reference point. For this like antenna, the physical 0 point of the antenna would be the bottom of the antenna and in the middle. However, the signal which is actually measured by the antenna itself is not related to this antenna reference point, but it is azimuth and elevation dependent where you actually measure the point. This I try to show you in this graphics here on the right. So here we see a satellite, it sends the signal. It's the red signal is for L1. Then we have a zenith and azimuth dependency. So we have a phase variation, which we have to correct. So we get kind of to the phase center offset, and then we have to correct or add also taking into account that we have this phase center offset, which goes to the antenna reference point. And then finally, you then also have to take into account, of course, from the antenna reference point to go to your marker position. And here, as you can see in this plot, then we have the yellow one. This would be the case for the L2 observation. So here we see that it's not only directing, depending on the direction, but we also have a frequency dependency of this phase variation. So we cannot just use one calibration for all signals. Now the pattern itself consists within the IGS. So we have a phase center offset. This is a nadir and azimuth independent part. However, it's the same value which have to be applied for all measurements, but you still need to take into account from where your observation is coming from. And then we have the second part, this is the phase variation. This is then actually the elevation and azimuth dependent part. So basically this is kind of a grid. And for each azimuth and elevation, you have then a different value which you have to be addressed or have to apply in order to correct for this distance to your antenna reference point. It has to be said, of course, that the full pattern is the combination of the phase center offset and the phase variations. And also I would like to mention that the separation to this phase center offset in this phase variation is completely arbitrary. So the IGS has its definition for most of the receiver type calibrations that the phase center offset is defined in such a way that the 90 degrees zenith angle of the phase variations is 0. One could but also think of other options that to say we have a 0 mean condition over all phase variation, or one could even omit the phase center offset and say we take everything into the phase variation. Now I would like to also show you a bit of some examples of the patterns that we use. So these patterns which we use within the IGS are so-called type mean calibrations. So we don't have a calibration with each individual antenna, but we take a samples of at least 5 antennas. They are calibrated, and out of them, one creates a type mean calibration, which can be used for all antennas of this type. Here we see now an example for a Trimble antenna where we have these patterns. So we have here the patterns of L1, and we here have a scatter, or the phase variations are, let's say, plus minus 50 millimeters. For L2, the phase variation in this case a bit smaller. However, you have to consider that in particular for PPP and other methods, you usually are not using directly L1, L2, but you're using some linear combinations. For example, in the case of the ionosphere-free linear combination to get rid of the ionosphere, you have a combination of roughly 2.54 times L1 minus 1.54 L2. And then it can happen that the combined corrections are rather much higher compared to the individual calibrations. It might also change the pattern itself, as it is a linear combination. And on top of that, we also have then the phase center offsets. In this case, usually for X and Y, they're rather low. They're about 1-2 millimeters, but the Z offset is about 90 millimeters for L1 and 120 meters for L2. And for example, if you create here now the ionosphere linear combination, you will get an offset of 45 millimeters. Then we have an example for an Leica antenna. Here we see the variations much smaller. This plus minus 5 millimeter. Again, if you form then again the linear combination, we see that you actually have higher phase variations, which you have to consider as if you just process, for example, L1. And again, here we see we have, for example, a bigger phase center offset. That's why it's very important to introduce it. It also has to mention you don't only have to use them for the ionosphere linear combination, but you also need to take into account if you do other linear combinations. And with this, I would like to come to the second part of this equation. So if you produce or calculate the geometrical distance, we don't only have to address actually the receiver station, but we also have a satellite which is transmitting the signal through an antenna. And here I would like to highlight that the satellite positions which are obtained by the IGS, that the position of the satellite is actually not connected to the center of the antenna, but it's actually the center of mass of the satellite. So if we look now at this picture, this is also not in scale, of course. So we have here the satellite, which is flying around. The satellite, the orbit itself is kind of given by the law of celestial mechanics. So here one can imagine the satellite is more or less fixed. Then you have the phase center offset between the center of mass to the actual transmission point of the signal. Here I have ignored the phase variations, but you also have to consider that you have different phase variations depending on the angle where the signal is actually received. Then it goes down to the receiver. There you're recepting it at the point. Then you have to correct for the phase variation. You connect for the phase center offset, and then you actually get the coordinate or the point of the antenna reference point, which you can access in real time, or really you can access it physically. And what I would like to point out a bit with this picture is that we have here the Earth. It's a rather small Earth compared to the satellite, but we see here that we have the scale of the satellite. So this would be the Earth scale. Then we have the coordinate, and depending on the scale of the Earth, this coordinate can vary, in particular for the height. And as you can see, we have a direct correlation between the phase center offset of the satellite, the phase center offset of the receiver, and the scale of the Earth. So this means if you would blow up the Earth, then the coordinate might go up, and this can then be fully absorbed or almost fully absorbed by the phase center offsets. It's not a one-to-one correlation, but you have a very high correlation. Therefore, it's important that you always, or basically, we cannot estimate the phase center offset of the satellites and the scale without any a priori information. And now I would like to go to the phase center variations. And here we see that I have the patterns of a Galileo IOV satellite. I'm just back. So I'm sorry, but I had some technical issues that the stereo just started to run without my permission. So we see here then the satellite patterns of the FOC IOV satellite. Here we have not 90 degrees, of course, but this is really the field of view of plus minus 14 degrees. And here again, we see the pattern for E1. This would be the pattern of E5. And if you do then make the linear combination, you get the pattern E1, E5, which rather looks a bit different than the individual patterns. The patterns of the for the E1, for the satellite E2010, this would be an FOC satellite. Here we see that the phase variations are rather smaller than compared to the IOV satellites which I have shown. But again, we see the patterns of the E1, E5, and then again, it looks a bit different if you form actually the linear combinations. And with this, I would like to this was the summary about the phase center offset itself. And now I would like also to mention how do we get this antenna calibrations. So for the receiver antenna patterns, basically they're based on calibrations. So the IGS relies on robot calibrations on the one side. These are calibrated using robot systems. And this is done using real measurements. So the robots are outside and you track the satellite. The other method would be using chamber calibrations. These are calibrated in anechoic chambers, where you actually measure the data or in these chambers itself and not with real satellite data. For the satellite patterns, this is rather different. So here we have for the IGS 14 antennas up to them, basically the phase center offsets were not available, so they have not been disclosed by GPS nor GLONASS. So the phase center offset had to be estimated. As mentioned, we have a high correlation between the scale, the basic ITRF scale, and the phase center offsets we had, or basically the ITRF scale was taken, fixed, and then estimated the phase center offsets which correspond to the ITRF scale, so that when you use this phase center offset, you are able then to retrieve PPP coordinates which are in the ITRF scale itself. And in addition, we also estimate blockwise phase variations. Here I would like to mention that we just estimated nadir dependencies, so there is no azimuth dependencies. And these phase variations are going for plus minus 1 to 2 centimeter variation through the nadir angles, which we estimate. Here I would like to note that in particular that we are only estimating phase variations for the ionosphere free linear combination. This then basically results that in the amtex file which we deliver, L1 is equal L2, which is equal to the ionosphere free linear combination. If we actually have now the disclosed patterns for Galileo QZSS, which have been released, there we have the full patterns for all frequencies. Currently Beidou, and for the GPS Block 3A satellites, they are also released the phase center offset without the phase variations. So this is now the current situations which we are. So we are currently in the IGS 14 reference frame. So here we see we have the estimations for the GPS and GLONASS satellites, and we have calibrations for the receivers for GPS and GLONASS. For the IGS 20, which is not yet released, there we have now the Galileo, which is part of the IGS 20, where we have the satellite calibrations. For GPS and GLONASS, they are still estimated. However, for GPS, we have the Block 2A, where we actually have the estimated offsets. On the receiver side, we now have multi-GNSS calibration, so we really can cover all frequencies. Here I would like in particular mention that the IGS 20 amtex file is not yet released. As mentioned, the phase center offset is correlated to the ITRF scale. This means it will be that we will adjust the phase center offset also of the calibrated values in order to match the corresponding scale, so that the user just has to use the amtex file without having to do other corrections, and you really get then the ITRF scale. Now this is, before I come to the end, I just give you a short overview of a test. So I made some simple PPP solutions for one day for station SIM3 in Switzerland, which uses a Trimble antenna. So I produced using the Repro 3 products with Galileo. So I've used a GRE solution, so all system included, which is the reference. Then I made a GPS solution, a GLONASS solutions, and Galileo solution. And here we see they're scattered around 1-2 millimeters. This can have various reasons why we scatter. It could be that, of course, we might have some discrepancies in antenna patterns. We have different geometries of the different systems, different numbers of satellites, and so on. However, for example, if we now use Galileo and without using actually the real frequency calibration, so instead of using E5, we're using L2, then we see we suddenly get an offset of almost over 1 centimeter. So this means if we have the IGS 14 antex does not include multi-GNSS calibrations for E5. Therefore, if you would just use it for the Repro 3, you would get an offset of about 1 centimeter. So this is really important. We use the correct calibrations. As also mentioned, that the phase center offset of the satellite is a crucial part defining the scale and therefore also the station height. If you would now use the Repro 3 product, which has its own scale, which is not consistent with the IGS 14, I mean, just take the products Repro 3, then use the IGS 14 antex for the satellites and the receivers. Then we get at the end an offset of 9 millimeters for a GPS-only solution. So here we already see that by using the Repro 3 products with the IGS 14 antex, we get inconsistencies between these solutions, where we see that those two are actually not really compatible, and you really have to be sure to use both, always the consistent pair. Now, what does the IGS provide to the user? As mentioned before, we provide the naming of the antennas. We also provide some schematic antenna graphics defining the antenna reference point, which includes the north orientation mark and the antenna reference point, which is defined in such graphics. We have the antenna reference point would be the bottom of the antenna, and the north orientation mark would be here. I think here is a north orientation mark. So here would be a mark on the antenna, but it could also be just a jack where you plug in the cable. But this is defined in this file. And last but not least, of course, we also have the antenna patterns itself, which you can use. So what you have to take out of this presentation, it's that the IGS products are based on the IGS antenna model. So if you use them, make sure you have consistent products with the consistent antenna models. Then the antenna patterns are azimuth and elevation dependent. So take the antenna orientation into account. And also I would like to mention that the antenna patterns are frequency dependent. So for example, you should not just use L2 for F5 in case you don't have it. And if you have your processing your own antennas, of course, you can check the IGS antex file and see if we have type info of your own antenna. If you do not have them, then you have to see maybe with the manufacturers or calibrate the antenna in some way to actually get its patterns to estimate coordinates. And with that, I come to the end of my presentation. And if there are any questions, I'm happy to answer them now or later.
Okay, thank you, Arturo, for this nice presentation. We have some questions in the chat for you. I think the first one is from Yang Hing Pan. I hope I have pronounced it correctly. Do you want to give it by your own?
Yeah, thank you. The pronunciation is almost correct. And my question is about that. Have you ever tried to estimate the PCV values for the, for example, GPS 3A, and then compare the value to the agency disclosed ones? How about the consistency?
Yes, I have made for the phase variations. They are not disclosed by the agency, so we just have the phase center offsets. So we have estimated the phase variations which are included. And for the phase center offset, the main issue is that within the IGS 14 antex, we have the scale which is given by the ITRF. So there we do expect that we have differences between the calibrations. However, what we have done to test how feasible are those offsets, we have made some tests by using the scale which is introduced by the Galileo chamber calibrations. And we have seen that actually the block 3A phase center offset fits quite well with the Galileo calibrations. So from this, it gives us a hint that those calibrations are actually quite feasible and quite good, and they're compatible to each other. However, I have to mention, we just have tested the ionosphere free linear combination. So we have not tested really L1, L2, or even L5 phase center offsets, just the ionosphere free linear combinations, and these close patterns actually seem to be consistent between Galileo and GPS.
Thank you.
Okay, there's another question from Alvaro Santamaria in the chat.
So hi, Arturo. So basically, we have been tracking Galileo for some years now, but still there are plenty of antennas that are missing a calibration for Galileo. So I guess you have talked a lot about this on the in the antenna working group. So is there anything we can do about that?
Yes, the first question, of course, to check for that. I'm not sure if you have access to the IGS Repro Antec. So there you can check there we have multi-GNSS calibrations for about 40 antennas.
Yes, exactly. The 40 antennas where there are like 400 antennas out there.
Yes, and for the other antennas, the problem is we don't have the antennas nor the capacity to make these tests. So there you are kind of, you have to make it as a user. You have to make these calibrations or ask the manufacturers to provide these calibrations. So usually these calibrations come through the manufacturers, they let it calibrate, and we then receive those calibrations. But the antenna working groups itself, nor the IGS has not the capacity nor the equipment to make those calibrations. Okay, we just make the collection.
I thought there were kind of volunteering people doing robot calibrations, but maybe I was wrong.
The IGS currently is making some, how say it, some tests, for example, some calibrations, tests, and so on. But maybe there are some groups, you might, if you have some antennas, you can ask also the antenna working group, and then we can ask around if some facilities might be interested to do so.
Okay. Thanks.
Okay, then we have Ante Octavian with another question.
Hey Arturo, thank you for your presentation. I was a little bit curious about the ionosphere-free combination offsets and variations you presented there, because that's not a direct observable. So can you elaborate a little bit how actually it was computed?
Yes, you're meaning for the satellite offsets.
Yeah, exactly.
Exactly. The main problem is, or issue is, that for the satellites itself, we don't have any calibrations. And this means we have to estimate those. And we estimate those, and different ACs are estimating those. However, when you estimate the phase center offsets, we are actually using the ionosphere free linear combination. So we get only estimations for the ionosphere free linear combination because we use this observable. And as we only have these observations, this ionosphere combination, we cannot really separate then between L1 and L2. We just have the one for the ionosphere free linear combination. And the only way to map that in the Antex file is, for example, by just saying, we say L1 is equal to L2, because if you apply that, then for the EF combination, you will get the same result because it's 1.5 or 2.5 minus 1.5 with the factor. So we end up with the same value. And if you would estimate a geometry-free linear combination, it cancels out. So then it's like you have no observations, no phase center offsets itself. That's how it's done, and that's why we have L1 equals L2. Does this answer some of your question?
At least the curiosity, it's fulfilled. Thank you.
Okay. So then we have from Carlos Gonzalez a question to Arturo?
Hello, this is Carlos Gonzalo from IGS. So the question is related, maybe I have mentioned, maybe I missed. So when is it foreseen to release these IGS 20 antics files? Because, well, in fact, it's just a matter of software update, because our software currently considers the same values. It does not take into account the satellite, only the block for GPS satellites, assuming that they have the same values for both frequencies, or even the three of them in case of block 3. So, and I suppose that you have said that this could change from ES 20.
Yes. Well, as I mentioned, of course, for GPS and GLONASS, there still will be just a ionosphere linear combination because we don't have those values. The release will be combined with the actual IGS 20 release. So this will take, as Tom has said already before, this will take somewhere in 2022. So I cannot really say when. It will be, it's a crucial part of the IGS 20 solution, which we released. However, if you just would like to have it's not a preliminary, we have the Repro 3 Antex, which includes the multi-GNSS part, then you can write me and I can send you that file. But it has to be mentioned, of course, that these values are not the values which will be finally used for the IGS 20, as it has a different scale. It will not be the scale induced by those offsets, which actually will be used then by the IGS 20.
Okay, thank you very much. Well, thank you for your proposal.
And then we have another question by James Woodburn.
Yes, my question, thank you. My question is related to, are there antenna phase center variation patterns available for user satellite-based GPS receiver antennas, as opposed to receivers sitting on the ground?
Well, from the IGS side itself, no, we don't maintain those calibrations. But of course, for LEO, if you particularly refer to LEO satellites, there are patterns available from the agencies which run those satellites, at least for some of those. But we do not collect them currently at the IGS. So there you would have actually to ask then the corresponding agencies which operate those antennas.
Okay, thank you.
Okay, are there other questions? Then the schedule says now that we have 10 minutes break, but we have taken already 4 minutes from the break for this question round. But I think 5 minutes is enough for maintenance. And we continue in 5 minutes from now.